So far, we have discussed about the various processes by which breakdown happens in the different kinds of medium, like gases, liquids, solids. We have also discussed about vacuum insulation. Uh, we are still left with one of the most important kinds of insulation that we use in practice, and that is composite insulation, where we don't have just one single medium or one single kind of dielectric medium. We have a combination of at least more than one. When I talk about composite insulation, there can be two kinds of composite insulations that we are talking about. First is where you have a gaseous medium with a solid or a gas or a liquid, and the other kind is where you have the same kind of medium but two different materials. So a solid with a solid, a liquid with a liquid, or a gas with a gas. So this is also an example of a composite insulation. Why do we use composite insulation? Remember, I have kept telling you that when we choose insulation, we do not choose insulation only for its electrical or dielectric properties. When we are choosing an insulation for a particular application, we are also interested in providing certain electrical, certain non-electrical features. For example, it could be mechanical, thermal, radiative, and other factors which can cause insulation destruction. And therefore, it might be necessary to use a combination of different kinds of materials or different kinds of media. So we very often combine various complementary dielectric media. For example, you can use solid dielectrics because it has a structural strength, and at the same time it can withstand high electric stress, but solids cannot fill up the entire space between conductors, and therefore in order to eliminate voids, we might incorporate gases. And if our objective is not only to eliminate voids, but also to provide cooling capabilities, then we might use liquids. We've already discussed these things. We have talked about transfer oil, we have talked about voids, etc. Examples of, then there are multi-layers insulations where you use solids but use different layers of different materials. The example is glass mica multi-layer insulation, where you have mica and you have layers, you have glass and you have glass interspersed with mica layers. Or you might have epoxy, glass mica multilayer insulation, which is impregnated with epoxy composite. So we want to make rod insulators, and for that we take glass mica multilayer insulation, and over and above that we use epoxy impregnation. Oil paper insulation is very commonly used. It is used as capacitor paper. When you have any paper, if you take a piece of paper and if you look at it, if you hold it very close to the light, any ordinary paper, if you hold close to the pipe, you will see that there are a lot of voids inside. You can see a lot of irregularities, and these irregularities are because there are air voids inside the paper. So it's not a uniform throughout the volume of the paper. You do not have uniformity. There might be some regions which are thinner, some regions which are thicker, and you might have voids voids incorporated between the two layers. Now, whenever you have voids in between two layers, there can be a problem. And what we do is sometimes we take this paper and we impregnate it with oil. What this means is that wherever you have voids which are filled with air or gases, when you impregnate that with oil, these voids now become filled up with oil. This gives better property because oil has a higher dielectric strength than air. What can happen is, if you have a void of gas or air inside a solid material, that particular void can break down because the breakdown strength of the gas is lower than the breakdown strength of the paper, solid material. So you use, instead of air, you use liquid, you use oil, which has a higher breakdown strength. But does this solve the problem? Do we still retain certain problems simply because instead of using a homogeneous material, you are using a composite dielectric? So let us see what is the problem that we are likely to face when we have composite insulation. First, let me take the simplest example. I always take the case of the capacitor because a capacitor behavior is well known to all of us. So let's say I have a capacitor, an ideal parallel plate capacitor, and let's say I have initially air. This entire space D between the two is filled up with air. And let's say air is epsilon 1 permittivity. Now, imagine that I want to stress this capacitor to higher voltages. What would I do? I would replace air with some other material. Let's say I would replace it with some solid material which has a higher permittivity of epsilon 2, and that would give me better properties. Now let us imagine, for whatever reasons, I mean, these do not have to be realistic reasons, just let us consider the case where instead of being able to replace the entire gap distance, the air in the entire gap distance with a solid material epsilon 2, let's say I don't have enough money and I have only a block of material which has a thickness D2. So I put it inside. Okay, I would like to fill the entire space D. I'm not able to do that, so I'm going to make do with what I have. And what I do is I fill up to distance D2 with a material which has a higher permittivity epsilon 2. So there is still a distance D1 which is left with air or whatever material we started with, which has a lower permittivity epsilon 1. Is this a better situation or is it a worse situation? The question I'm asking is, if I have a capacitor where the entire distance D between the capacitor plates is filled with a gas or a lower permittivity material epsilon 1, and I think it is inadequate for my purpose, if I replace the entire region D with a material of permittivity epsilon 2, obviously it's going to be better. But here I have a strange situation where I have only been able to replace up to D2 distance a material of permittivity epsilon 2, and for the remaining D1 I'm still left with epsilon 1. I would imagine that this may not be as good as replacing the entire material, filling up the entire material with epsilon 2, but maybe it's better than having epsilon 1 all over the place. Is it? Let us look at this. So what happens is I have a voltage V applied across the material. So across material epsilon 1, I have voltage V1, and across material epsilon 2 of thickness D2, I have voltage drop V2. Of course, V1 plus V2 must be equal to V. Let us imagine that the electric flux in epsilon 1 is D1 and electric field is E1, D2, E2. So these are the flux densities and the electrostatic fields in the two materials. Now let me also assume that there is no free surface charge at the interface between these two materials. So there is no accumulation of free charge. We're not talking about bound induced charges. In which case I should be able to write, now D is equal to epsilon E. So therefore D1 is equal to epsilon 1 E1 and D2 is equal to epsilon 2 E2. And at the interface, if there are no free charges, it means that D1 must be equal to D2. So if D1 is equal to D2, then I get this relation E1 by E2 is equal to epsilon 2 by epsilon 1, which means I will see different electric stresses in the two materials, and the stresses on the material is also governed not only by the permittivity of that material, but the permittivity of the neighboring material. So for example, if epsilon 2 increases, the stress in E1 in the material epsilon 1 will change. If I don't do anything to this material, but I change the material, epsilon 2, higher is epsilon 2, higher is epsilon 2, higher is E1. So the electric field that you see in material epsilon 1 will increase if the permittivity of material 2 increases. Okay, this is a important concept where you understand that the stress, the electric stress in a dielectric medium not only depends upon the applied electric field, not only depends upon the dielectric constant of that material, but it also is governed by the dielectric constant of a neighboring material. Now V is equal to V1 plus V2, so V is equal to E1 D1 plus E2 D2. These are uniform fields because we've considered an parallel plate capacitor. This is also perfectly parallel. This is just for ease of understanding. So then I can obtain an expression for the electric field stress in material epsilon 1, which is given by E1 equal to V, that is the total voltage across the two capacitor plates, divided by D1 plus D2 into epsilon 1 by epsilon 2. Now, if you look at this, when I had the entire space D filled up with epsilon 1, my electric field E1 was equal to V divided by D1 plus D2. And now I have the modified electric field in the material epsilon 1 as V divided by D1 plus D2 into epsilon 1, epsilon 2. Epsilon 1 is smaller than epsilon 2. We have assumed we are replacing this region with the gap dielectric with a material of higher permittivity, which means epsilon 1 by epsilon 2 is a fraction less than 1, which means the denominator is reduced now. D1 plus D2 into a fraction is less than D1 plus D2, which means that this denominator now represents what is called the effective gap distance. We started with the gap distance D1 plus D2. We now have an effective gap distance D1 plus D2 into epsilon 1 by epsilon 2. So the effective gap distance is determined by the ratio of the permittivities of the two materials. So now therefore E1 will be higher than initially, which means that if initially the material was not going to break down, now for the same voltage V, the material might break down because the electric field E1 in epsilon 1 may exceed the dielectric breakdown strength of the material. And where do you have the worst case scenario? The worst case scenario happens when you have filled up this entire space almost, leaving an infinitesimal gap, which means D1 is smallest possible. So when D1 is minimum, the denominator will be minimum because the effective gap distance will be minimum, and the electric stress in the material will be maximum. So you have a situation, let's say you have a material, you have a conductor, and inside that you have a solid. Now this conductor has to be perfectly bonded. So let's say this is my insulation that I'm going to use, and let's say I'm going to use metal plate on top of it. So I just put the metal plate on top of this. Even if I do not make sure that there is proper bonding at the surface of the two metals, there will be an infinitesimal air gap between the two materials. As a result, you will have a very small infinitesimal gap distance D1, which is filled with, let's say, air, permittivity epsilon 1, and here electric field E1 will become very high. And there may come a situation where this E1 will exceed the breakdown strength of the air in this infinitesimal region, and there will be partial discharges. There will be discharge in this region. And when there is discharge in this region, by processes that we have not yet discussed, if you have partial discharges inside a solid, ultimately it can lead to complete breakdown. So once you have, just to give you an idea, if there is discharge in this air gap, there will be production of charged particles which are accelerated in the field. Those charged particles will impinge on the second dielectric material, and by some complicated processes which we will discuss later, they can damage the second dielectric material and can lead to complete catastrophic failure of the entire material. Even if it doesn't lead to complete failure, it will reduce to decreased functionality. you will have an inferior capacitor than you bargained for. And that is why whenever we use a solid dielectric and we use a metal contact, we make sure either that there is perfect bonding. So you have to do some bonding, let's say you put some epoxy so that it perfectly bonds with the material. So there has to be proper adhesion. Or you put a very high pressure. You can put very high pressure on top of the electrode so that the gap is reduced. So this is a very important, where even if you do not talk about composite materials, but even if you are talking about homogeneous dielectrics, contacts become very important. The dielectric conductor contact may become very important and can become a seed for discharge and ultimate failure because of this reduced effective gap distance. So effective gap distance reduces to this value. So any partial replacement of the gas. So we are talking about contacts when we are talking about D1 becoming very small. But let's say you design an insulation where because of whatever reason, you only replace part of the inferior dielectric material with a material with higher permittivity. This will possibly not improve the dielectric strength of an air or gas insulated system, because the gas will now become more stressed than the original situation. Of course, the higher permittivity material may not break down immediately or so easily, but the original low permittivity material, whether it is air or gas, will break down, will discharge, and that can lead to catastrophic failure of the whole situation. So as I said, the worst case is displayed for conditions when D1 tends to 0, that is for very thin layers of low permittivity material. So you should always avoid adjacent layers of materials with very highly disparate permittivity. If epsilon 1, you have a layer of epsilon 1, do not place next to it a layer of epsilon 2, which is very dramatically different from epsilon 1. You can try to grade the layers so that you have epsilon 1, then a little more than epsilon 1, then a little more than epsilon 2. This kind of situations are there, and we will talk about this later. These are called functionally graded materials. So right now the point I'm making is that you should not use materials with very high disparate permittivities next to each other. Sandwiched or multi-dielectric insulation systems can therefore be dangerous if the layers of very different permittivities, and as I already explained, metal dielectric contacts can be cause for concern. The other situation is where you have a material, and inside the material you have a combination of various permittivities. You can have layers, or you can have uniformly distributed filler particles. And whenever you have that kind of a composite insulation, there are very many reasons for which we use composite insulation. Maybe let's say you have epoxy, and epoxy is a cheap and very dependable insulation, but it does not have very good structural property. So what you might do is you might take it does have a reasonably good structural property, but let's say you want to improve the structural property. So you might put in between mica layers, or other materials can be there. So you can use several layers of different materials, or you can take epoxy and incorporate that with micro-sized fillers. We actually do that. So when we are building bushings with epoxy resin is a polymer which is very commonly used for the creation of bushings. And what we do is, when we use this epoxy, before using it in the bushing, we incorporate micro-sized metal oxide particles. The result is that the structural integrity of the epoxy increases. So you have a composite material which is no longer homogeneous, and you have two different materials uniformly distributed. In which case, what is the permittivity of your material? To understand the behavior of the material, you have to conduct tests. So you will have to separately figure out what its breakdown strength is. Its breakdown strength may not have any relation with the breakdown strength of either the filler or the matrix material, the epoxy. Or if you have layers, then it will have some kind of a relationship, but we would need to know what is the again, in the breakdown, strength may be completely different, but permittivity will depend upon the constituent layers and the constituent materials. But what you would like to understand is you would like to treat that material as a homogeneous material with an equivalent permittivity. So here we talk about effective permittivity, and effective or mean value of the permittivity of any homogeneous mixture of dielectric materials. So it can't be if you have a heterogeneous material, but let's say you have a composite which is more or less homogeneous. So let's say it's epoxy with always you have 30% volume fraction of let's say aluminium oxide, which is evenly dispersed throughout the material. Now if you want to understand how this material behaves, we will separately conduct breakdown tests, but you can compute or predict what kind of permittivity or dielectric constant this composite material will have. And when I talk about the effective dielectric constant, what I mean is, if you imagine that this composite was actually homogeneous with only a single permittivity, then what would be the permittivity of that homogeneous material so that it behaves identically as this composite material? For example, if you have resin impregnated paper or oil impregnated craft paper, you would not go around measuring the permittivities of the oil and the paper separately. You would like to understand how the composite behaves. And one of the ways is to characterize it with its effective permittivity. Now here I'm just going to talk about parallel layers because I'm just trying to understand what happens. Of course, even if they're not parallel, we can calculate, but I'll not talk about that now. Usually the layers are oriented parallel to the electrodes. So let's say, as an extension of our previous discussion, I have a two dielectric system and I'm subdividing this into a number of parallel layers. So here we had just two layers. Instead of that, I have several layers, epsilon 1, epsilon 2, epsilon 3, epsilon. I have several layers of parallel layers. What should I have in this situation? In the same manner as we obtained the permittivity of the previous two dielectric material, you can calculate the electric fields and you can calculate the flux densities. At every interface, D is equal, because we are assuming that there is no free surface charge at the interfaces between the dielectrics, in which case we can consider an effective flux density D is equal to epsilon resultant, that is your resultant or effective permittivity, into capital E. So the effective permittivity is essentially the ratio between the total flux density and the average field stress inside the material, and this will also be equal to D in every material. So it will be equal to epsilon 1 E1 equal to epsilon 2 E2 and so on and so forth. So for the two dielectric system, I can write D is equal to epsilon res E, epsilon resultant being the permittivity, a fictitious permittivity, which is the ratio between the flux density and the average field intensity within this composite material, and this will be equal to the D in every flux density in every layer, provided there is no interface, no free charge at the interfaces of these layers. So E res is equal to epsilon 1 E1 equal to epsilon 2 E2. So I can write down epsilon resultant into E is equal to V by D divided by 1 by D1 by D epsilon 1 plus D2 by D epsilon 2. Where therefore I can compute the resultant permittivity as equal to V by D cancels out both from the left hand side and the right hand side. So E is equal to average electric field, E is V by D. So I can cancel that out from the left and right hand side. Look at this. If you consider these to be parallel layers, then D1 by D is the same ratio as their volumes, because the area of each layer is the same. So D1D, which is the fractional distance, will be equal to the fractional volume, and therefore D1 by D can be represented by V1, where V1 is V1 by volume of the first layer divided by the total volume. So it's a fractional value. V1 is not the volume of the first layer, but it is the fractional volume of the first layer. That is, it is the how much fraction of the total volume is taken by material with permittivity 1. So therefore, my resultant permittivity can be calculated as 1 by V1 by epsilon 1 plus V2 by epsilon 2. Now, if I have n number of layers, it means that my resultant permittivity will be 1 by V1 by epsilon 1 plus V2 by epsilon 2 plus V3 by epsilon 3, so on and so forth, up to Vn by epsilon n, provided summation Vi is equal to 1. So these are volume fractions. This kind of assumption does not work for all systems. This works only for finite parallel layers. What happens when we do not have finite parallel layers but we have uniform dispersion? We will discuss later. For the moment, we will stick with parallel layers. Now, what happens about the breakdown? How do these materials break down? These materials, as I said, will not really, the breakdown strength of the composite will generally not depend, not be predictable from the dielectric breakdown strengths of the individual components. And that is because the breakdown mechanism may be very different in a composite insulation than in a solid. As you know, if you have a solid, let's say you have a very pure solid, it will break down either under intrinsic breakdown, as I said, that is theoretically possible, or maybe there will be thermal breakdown, or there may be a tracking breakdown. These the kinds of things might happen. But when you have these two solid materials, let's say pure solid materials pressed next to each other, the dielectric will break down can break down due to various factors. Distortion of electric field in one dielectric due to the dielectric constant of the other. As I say, the electric field E1 changes if the permittivity epsilon 2 changes. And then so far we have been considering that there is no free charge. There might be free charge. There might be contacts. There might be air gaps. So many things can happen. And whenever there is a degradation or deterioration in one of the components, this can lead to deterioration or degradation of other components. So it is very difficult to predict the breakdown mechanism or strength of the composite material based on the individual insulating components, because there might be distortion of electric field in one dielectric due to dielectric constant of the other. Deterioration or degradation of one may affect the behavior of the other. These are just two examples of why we cannot predict, but there, as we go on along this course, there are many other factors that we will learn how insulating systems behave very differently from insulating materials of its constituent insulating materials, and that is something we will discuss later. So we have so far only considered multi-layer systems. Multi-layer systems, so that is one kind of composites insulation that we do use frequently. There are other kinds of composite insulation which we will discuss later. Multi-layer insulation systems are multi-dielectric insulation systems which are made of thin layers. And these thin layers may be well impregnated by fluids or even gases of high breakdown strength. And when you compare with air, one of the gases which has a very high dielectric strength is SF6. And the reason why SF6 has a high dielectric strength is that it is an electronegative gas. So when you have an electronegative gas, electronegative gases are gases where the molecules have an affinity for electrons. So if there are free electrons, neutral molecules will tend to capture these electrons and will become negative ions. Electrons move much faster. They can collide and ionize much faster. But when they're captured by neutral molecules and they become negative ions, they do not move as fast and they do not have that much colliding ionization capability. So in fact, what an electronegative gas does is it tends to remove electrons from the gas so that ionization to breakdown process becomes much more difficult. Now why do we use multi-layer systems? One reason is let's say you have a uniform material. Now, if you use a single material, there might be some weak points. There might be entrapped bubbles, entrapped gases. And in these regions, so let's see what I'm trying to say. Let me try and draw that. Let's say this is your single material, and in this single material, you cannot ensure that you can eliminate all voids. So maybe there are trapped air gaps, air bubbles, and they are there. Here, they are everywhere. Now, what happens is when you apply electric field across this, these gaps, these voids will contain materials with lower breakdown strength, and they will break down. And when these gaps discharge, this can cause ionization and collision, and by processes again which I will take later, the entire dielectric material can break down. And anyway, even if it doesn't break down, obviously you will not be able to apply very high electric stresses across this material as you might be able to apply across a section of the material which does not have any voids. Now let's say you cannot eliminate the voids, and or it becomes too costly. One is you fill up them or impregnate them with oil. That makes it better, but it still can break down. Still these weak spots are there. So what you do is you cut this material, and instead of having a single layer, you have multi-layers of the same insulating material. So what happens is this. So now you have a scenario like this. You still have the gaps, but these voids are now likely to be randomly distributed. So you do not have a single, it is not likely that you will have between the electrodes one large bubble, but instead you will have these regions cut off. So there is a small bubble here, but in the next layer you have solid material, bubbleless material, voidless material. Again in the next layer you have maybe here and here you have voids. So there is a less likelihood that you will have a conducting gap or a continuation of a weak region spanning the entire distance between the two electrodes. So single layers may have weak points of low breakdown strength. Overlapping of many layers will provide a statistical distribution of the weak points, and these weak points will not be spread throughout the gap distance, and this will ensure that statistically your material behaves better. Oil impregnated high voltage power cables are typical examples of multi-layer insulation systems. In a multi-layer insulation, it is not the breakdown strength which is of consequence. What is of consequence is the partial discharge level, and we will talk about partial discharges in one of the subsequent lectures. So composite insulations behave quite differently, and we have to understand many other processes before we can really understand how breakdown happens in composite insulation. But composite insulations are the most commonly used insulation materials. We hardly ever use pure homogeneous materials.